Welcome. Today, we're moving beyond textbook definitions to explore the deep trade-offs between Layer 4 and Layer 7 load balancers. This isn't just about features. It's about performance, cost, and designing truly resilient systems at scale. By the end, you'll understand why choosing the right one is critical.
Video streaming service versus an API gateway. Which load balancer for each? Many candidates default to L7 because it has more features, and that's where they falter. The real answer reveals a fundamental understanding of system architecture. The confusion starts because we're taught what they do, not the cost of what they do. Let's dissect that cost.
Every L7 feature comes with a performance tax. Inspecting a URL means parsing HTTP. Header-based routing requires buffering the entire request, consuming memory. And SSL termination is a notoriously CPU-intensive cryptographic operation on every single connection. When you're handling millions of requests per second, these seemingly small costs compound into significant latency and a much larger infrastructure bill. Layer 4 load balancers are simple and brutally effective. They operate at the transport layer, looking only at TCP or UDP information, like source IP and port. They make routing decisions in microseconds because there's no application data to parse. For workloads like video streaming, this is perfect. A user connects once, and then a high-throughput stream of packets flows for minutes. Optimizing that single initial routing decision with L7 is wasteful. Raw throughput is king, which is why systems like Netflix's OpenConnect CDN rely on this principle. Now, consider an API gateway routing requests to different microservices like /users or /orders. An L4 load balancer is blind to these paths. It literally cannot perform this function. Here, the overhead of L7 is not just justified, it's required. L7 allows you to manipulate requests by adding auth headers, perform granular health checks on specific endpoints, and implement critical security features like likelet limit. Companies like Stripe depend on L7 because every one of these intelligent features is essential for their business logic. Let's put them side by side. The latency difference is stark. Microseconds for L4 versus milliseconds for L7, which can be a 1,000-fold increase. This directly impacts connection per second capacity. L4 health checks are basic. Is the port open? While L7 can verify if an application endpoint is actually healthy. And that SSL termination point is crucial. Offloading it can consume up to 60% of an L7 load balancer CPU, a cost L4 completely avoids by passing it through. Here's the nuance that most discussions miss. Large-scale systems rarely choose just one. They use a hybrid approach. Think of Discord's architecture. They use L4 for their real-time voice and video traffic where low latency is critical, but L7 for their REST API, where routing and authentication are needed. Even cloud providers model this reality. AWS offers the network load balancer for L4 workloads and the application load balancer for L7. The existence of both products is intentional, not legacy. So, let's return to that interview question. For video streaming, the answer is L4 is the choice. Video streams are long-lived connections where raw throughput and microsecond latency are paramount. The routing decision is made once. For the API gateway, definitely L7, we require path-based routing, header inspection for authentication, and granular health checks. The millisecond overhead is a necessary trade-off for these essential capabilities. Then add the expert nuance. In a real-world system, we'd likely use both in a hybrid architecture. The gap between theory and practice becomes crystal clear when you observe these systems in action. Running both load balancer types side by side in a demo environment is incredibly insightful. You can watch an L4 balancer forward video chunks with minimal latency, while an L7 balancer intelligently routes API requests by path. Seeing the real-time metrics and packet flows solidifies the intuition behind these architectural choices. I encourage you to build this for yourself. Ultimately, there is no single best load balancer. There is only the right tool for a specific workload. The core principle is to analyze your traffic characteristics first. Understand the performance cost of every feature you enable. By matching the tool to the task, speed for high-volume streams, intelligence for complex application logic, you design systems that are not only performant and resilient,